India's historic landing at the lunar South Pole. Now, global partners unite for the LUPEX mission, unlocking water ice for sustainable space exploration.
For decades after the Apollo missions, the scientific consensus was rigid. The moon was a dry, dead vacuum. When astronauts brought back these porous, crystalline lunar rock samples, researchers did find trace amounts of water trapped inside, but they dismissed the findings as Earth contamination introduced during the handling process. Now, as space agencies finalize plans to send humans back to the lunar surface and eventually to Mars, that assumption presents a massive logistical hurdle. Water is heavy, and hauling every drop required for a long-term mission from Earth creates a weight bottleneck that makes deep space travel nearly impossible. Local lunar water would solve this by doubling as fuel. By splitting these molecules into liquid hydrogen and oxygen, engineers can manufacture high-efficiency rocket propellant right on the lunar surface. This satellite mosaic of the lunar South Pole highlights the terrain where this ice might be hiding. Because the moon has almost no axial tilt, sunlight never reaches the floors of these deep craters. These permanently shadowed regions act as deep freeze traps, where temperatures remain low enough to hold water ice for billions of years. Confirming these ice reserves means future missions could finally stop hauling every kilogram of life support and fuel from Earth, relying instead on the resources already waiting at the destination. The first major breakthrough happened in 2008 with India's Chandrayaan-1 orbiter. The mission intentionally dropped a 35-kilogram moon impact probe directly into the Shackleton crater. As the probe slammed into the surface, its mass spectrometer detected water signatures in the plume of dust kicked up from the floor. While the crash proved water existed in the dust, the mission needed to map its distribution across the wider surface. To do that, the orbiter used the Moon Mineralogy Mapper, or M3. This chart shows an infrared light spectrum tracking how different materials absorb light. By analyzing these specific, measurable absorption signatures, the M3 instrument can distinguish between liquid water, vapor, and solid ice. This circular polar map displays the final results of that analysis. The blue shaded regions show the exact concentrations of water-equivalent hydrogen M3 discovered, mapping widespread surface ice in the shadowed craters and hydroxyl molecules trapped within the lunar soil. Chandrayaan-1 replaced decades of orbital speculation with specific coordinates, providing the first map of where humanity might actually find water off-world. But surface frost isn't enough to sustain a base. Ice at the surface is thin, and it's constantly exposed to micrometeorite bombardment and slow sublimation into the vacuum. For long-term use, scientists needed to find deeper, better protected reserves. That search was the primary goal of the 2019 Chandrayaan-2 mission. Its orbiter carried a dual-frequency synthetic aperture radar, or DFISAR. Microwaves fired into shadowed craters penetrate dusty soil, bouncing signals off buried material to locate hidden ice. To confirm ice instead of rocks, Chandrayaan-2 successfully isolated a highly specific return signature, a circular polarization ratio over 1, combined with low polarization. The radar data confirmed that the water at the poles isn't just a light dusting, it's a deep, viable reservoir capable of supporting industrial extraction. In August 2023, India moved from orbital mapping to surface analysis, becoming the first nation to successfully soft land a spacecraft near the lunar South Pole. The Vikram lander deployed the Pragyan rover, which used its CHAST instrument to take the first ever direct temperature profiles of the polar soil. This allowed scientists to see exactly how the local environment preserves these frozen volatiles. To find out what the soil was actually made of, the rover used its LIBS instrument. By firing high-intensity laser pulses, the instrument vaporizes tiny patches of soil into a brief, bright flash of plasma. The instrument then reads the light wavelengths to identify the exact elements in the dirt. The data revealed an unexpected element in the polar soil: sulfur. Sulfur is a volatile element that usually boils away under solar radiation, and its presence indicates that it has been trapped in the cold for a very long time. The discovery of sulfur suggests these polar craters have functioned as stable cold traps, shielding ancient volcanic gases from solar heat and preserving them for billions of years. With the ice mapped and the chemistry analyzed, the focus is now shifting to physical extraction. This rendering shows the upcoming Lunar Polar Exploration Mission, or LUPEX, a joint venture between ISRO and JAXA designed to physically process those reserves. LUPEX moves the operation from remote mapping to active prospecting. The rover will use a neutron spectrometer to hunt for high concentrations of buried hydrogen from the ground level. Once it locates a target, it will deploy the REIWA instrument. This CAD diagram shows the payload's internal mechanics, designed to excavate and heat lunar soil to extract physical water. By moving soil through these heating and weighing sections, the system measures exactly how much water can be extracted, verifying the yield for future settlers. By moving from orbital mapping to physical analysis, these missions have documented the Moon's transition from a barren rock to a viable outpost, the first link in a self-sustaining supply chain beyond Earth.